let people jump into. So hopefully I can do that here. My name's Adrian Harpold. I am an assistant professor at the University of Nevada in Reno, and am the PI on a project that's funded by the Southwest Climate Adaptation Science Center. That is really the uniting force for this work and the group that we have here. And so we wrote a proposal that was funded by the Southwest CASC. At the time, it was the CSC. That included a group that was Mike Dettinger, who at the time was at USGS, Seshwat Rajagopal, who at the time was at DRI, Steph McAfee at UNR, and myself. And then really the star of the show, Joshua Sturdivant, who's the master student who's just defended on the project. And so the original intent of our work was really focused around this alluring but somewhat vague idea of snow drought and how snow drought affected water supply forecasting. As good projects often do, this has morphed, and because we have such a great student, has really turned into a much broader investigation of water supply forecasting. And we've had some interactions along the way. We started with a really great relationship and feedback from the NRCS climate and, the folks up in
National Water and Climate Center.
Thank you, Josh. And they have been really a partner throughout a lot of this, but have also now interacted with the river forecast centers to some degree, some of the California agencies. And so our goals today are really to try to take your feedback, well, to, obviously give a presentation here. Josh is going to run through a very comprehensive and relatively dense rundown of what we did, but we really then are from our side are very interested in getting your feedback to make what we did better, and then make it more useful in whatever context that might be. So those are kind of our broad goals today from our end, are to make whatever we did better and more useful, especially from a sort of operational, practical sense, which is what I think a lot of this research drives to and benefits. So we're going to do about 40 minutes of Josh presenting. I think that's what he had in mind. Both Mike and I advised it to be as short as possible, but it is a lot to cover. And then we have an hour and a half, so we have till 2:30. But we'll see where the discussion goes. We have some prompts, but we'll see what the group might be interested in discussing. So with that, I'd like to turn it over to Josh Sturdivant, who's going to present really kind of two parts of, or two chapters or two pieces of work, however you want to think about it. Lately, they've been thesis chapters, but they're really two pieces of scientific work around these ideas.
All right, well, thanks, Adrian. I'm really honored to be able to present to you all today. Thanks for joining. It's been such a pleasure to work with Adrian, as well as the rest of my committee and the PIs on this grant for the last 2 years. So it's exciting to have the opportunity to try to get some of the science into the hands of the folks that use it. So with that, I'm going to be presenting today on seasonal water supply forecasting in the Western US, and specifically looking at those forecasts under declining snowpack conditions. So I guess I'll preach to the choir here, but really just try to lay out the narrative of our story and the information that I know that you all know. So precipitation that we've received during the winter is stored in snowpack, and this is really critical in bridging the divide between when that precipitation falls and when we need it most during these dry summer months. Snow water storage represents a significant portion of overall natural water storage, as well as our built water storage. And this makes it really critical in our water supply infrastructure in the Western US. Snow has been measured for the estimation of spring stream flow for well over 100 years. There's an interesting history that dates back to the University of Nevada, Reno. And one of the early pioneers of this method, Dr. James Church. And Church realized that by measuring snowpack on the summit of Mount Rose, he could predict the lake levels for Lake Tahoe the following spring and summer. This regression-based method is still widely used today by folks at the NRCS, California Department of Water Resources, and elsewhere, where manual measurements of snowpack supplement automated measurements as ways to estimate that spring and summer stream flow. However, our snowpack is certainly changing. Now, snowpack has always changed, and there have been low snow years, both on an interannual but also an interdecadal basis. And these can be described as snow droughts, which really come in two flavors. The first is a dry snow drought related to meteorological drought conditions, whereas the second is a warm snow drought stemming from increased temperatures. But these significant declines in snowpack that we have observed since mid-century across the Western US have been attributed to anthropogenic climate change. And these decreases in snow have implications for stream flow timing. In snow-dominated basins, peak flows that once occurred in the summer months are now occurring weeks or even months earlier. Now, these changes also lead to a more dynamic water management system, the reason why I'm sure many of you are here today and this conversation is happening, whereby changing snowpack can lead to both an increase in winter flooding events, but also an increase in summer droughts. And these two things together place a greater demand on our built infrastructure in our reservoirs and contribute to this reservoir managers bind, whereby managers must both maintain enough empty flood space in those dams to mitigate the risk of flooding, but also have enough water on hand to meet the demand during those dry summer months. If we look to the 2015 snow drought across the Western US and the Pacific states specifically, we can see these mechanics and dynamics play out, whereas a warm snow drought in places like Oregon translated into really peaky and high winter flows, which were followed by these summer low flows. In contrast, the dry snow drought in the Sierra Nevada, stemming from a larger meteorological drought, led to these below average stream flow conditions. Now, long-range stream flow predictions have historically benefited from the high predictive power of our winter and spring snowpack for the estimation of spring stream flow. But we have observed, of course, and project that there are significant changes happening underfoot to our snow conditions. We see that rain and snow lines are, of course, moving higher. There's more frequent midwinter melt events. We have more severe drought driven by some things such as increased atmospheric water demands. And these smaller snowpacks are also leading to slower snow melt, which has implications for groundwater recharge. And of course, there's also earlier stream flow timing. And so together, all of these pieces of our changing snowpack and stream flow generation mechanism in the Western US really raises this question of what are the implications for the skill of our forecasts and our models that we depend on for predicting spring snowmelt volumes. And so in this presentation today, I'm going to walk you through two studies. The first is a historical analysis of water supply forecasts. This was across the Western US, in which we recreated, evaluated, and compared two of the most common operational hydrologic models and looked specifically at their performance during low snow years. And to just give you the chase right up front, we found that statistical models like those used by the NRCS and others are generally more skillful than the conceptual models that we calibrated and used in this study. The exception being at long lead times and during below average snow years. We were also able to show that forecast skill is already declining. Our second study is an analysis of future water supply forecast skill in the Sierra Nevada, in which we simulated California Department of Water Resources forecasts using climate projections from 1950 to the end of the 21st century. And then we used this modeled environment to evaluate strategies for mitigating forecast skill degradation. And in this study, we were able to show that forecast skill is projected to continue to decline, and perhaps in a really significant way. But we did find some promising hope in simulated remote sensing of snowpack, where we were able to show that we are may be able to buffer loss of skill, notably at least through mid-century, after which point declining snowpack will affect our ability to improve skill through remote sensing, but soil moisture may offer more promise. The title of our first study was benchmarking statistical and conceptual seasonal water supply forecast models, implications for declining Western US snowpack. We asked 2 questions. The first, are water supply forecasts degraded during below average snowpack? And if so, what are the implications for these 2 types of models that we were evaluating? We answer these questions using a model benchmarking approach, where we'll compare these statistical models, which will serve as our benchmark, against these conceptual computer simulation models. We're going to answer these questions in series, beginning with the first. Our methods for this study pulled from the NRCS's statistical models, which are principal component regression models that use primarily snow water equivalent and precipitation to predict April through July streamflow volumes. The NRCS makes these forecasts or water supply outlooks across over 800 points in the Western US, and they use their snow telemetry stations along with those manual snow measurements, which measure SWE and P in the remote mountains to predict spring streamflow. These predictor variables from the SNOTEL stations are put through a principal component analysis and then regressed against spring streamflow volumes. And that looks something like this. And so in this study, we actually recreate these NRCS forecasts, although they are heavily guided by the official NRCS regression equations. There are 2 reasons for doing so. The first is that the official NRCS equations oftentimes use a variety of predictor variables, which lead to a more skillful forecast, of course, but make it really difficult to objectively compare across basins. And the second reason is that it's challenging to account for manual adjustments by forecasters whose objective, of course, is to produce the best forecast and not so much scientific repeatability. And so for these 2 reasons, we recreate these forecasts across 4 lead times predicting April through July streamflow volumes for water years 1981 to 2014. We're then comparing this model against a conceptual model from the National Weather Service. This model is the Sacramento Soil Moisture Accounting Model, or SAC-SMA, which is paired to SNOW 17 and uses precipitation and temperature to predict continuous streamflow volumes, which can then be aggregated to seasonal volumes. We run SAC-SMA using DayMet, which is a gridded product. We take precipitation and temperature data from the CAMELS data set and feed that to SNOW 17, which is a simple temperature index model, which partitions the precip into rain and snow, fed to SAC-SMA, which then simulates runoff and then eventually streamflow. So we issue SAC-SMA on this similar monthly structure of January through April, predicting those same April through July streamflow volumes for the same water years, except for the 1990s, which we use to calibrate the model. Specifically, we use an ensemble streamflow prediction technique, which consists of 2 steps. The first is the initialization of the model so that we can get the initial hydrologic conditions on the forecast issue date, after which point the model is then run with an ensemble of the historical meteorology, the mean or median of which becomes the prediction for April through July. We compare these models and evaluate them using a Nash-Sutcliffe efficiency, which is a metric measuring signal to noise. And specifically in this study, we use a bottom end bounded version with values ranging from -1 to 1. Going into the study, our research hypotheses were that regression-based models become less skillful under lower snow conditions, perhaps or because of their built-in linearity assumptions, but also because they're generally less dynamic and likely to be challenged by climate non-stationarity. In contrast, we hypothesize that conceptual models like SAC-SMA would also be vulnerable to loss of snow, but maybe would predict extremes better due to explicit parameterization or daily training of the model. But that across these two models, there would be instances where basins would likely be more buffered from loss of skill or more at risk. Our study basins for this first study were selected from the CAMELS dataset, which is a group of minimally impacted basins. And we found those which had forcing data available for both models, as well as basins which were existing NRCS forecast locations. We sometimes aggregate the results from this study into hydrologic unit codes, which include the Pacific Northwest, the Upper Missouri, the Great Basin, and then we lump together the Upper and Lower Colorado with the Rio Grande. Our workflow looks something like this, where we have our study basins, which are then run using the principal component regression models across 4 lead times in parallel with CASC SMA, and then we evaluate these with our Nash-Sutcliffe or other metric. This benchmarking approach allows us to gain a better understanding of the relative model capabilities, specifically during these low snow years. So our results from this analysis, if we look at the aggregated forecast evaluations across these 4 lead times, using this Nash-Sutcliffe efficiency, where higher values are more skillful, and each of these boxes represents all those basins across all study years, we see that the PCR model in white is more skillful than CASC SMA in gray, particularly at these longer lead times. We see that by April 1, there are larger differences between these two models. On the whole, however, we do find that they are generally within about 15 to 20% of one another. If we then run these models as a perfect prognostic, that is, using data through the end of the forecast period and then looking back, we observe that the PCR model has a higher optimal performance as defined by this perfect prognostic. And this represents a higher upper envelope of the performance, which we see that the model approaches by April 1. CASC SMA in comparison is more limited in its optimal performance as defined by this lower threshold. Our third finding is that if we subdivide our study years into above average snow years, that the PCR model is more skillful across all lead times, and particularly by April 1. And if we do the opposite with the below average snow years, we see that CASC SMA in dark red is more skillful than PCR in light red at these longer lead times, but that this pattern flips by April 1. We can then take all of these pieces and paste them back together and compare wet years and dry years. And we see that these wet years are more skillful than the dry years across all lead times. Now, to pull apart some important implications of this analysis, clearly these models are less skillful during low snow years, which is not all that surprising given that it's more challenging to predict a lower flow, which kind of represents a smaller target. But it does raise this question of whether or not these snow droughts are an analog for future snowpack decline or not. And some research would suggest that that is not the case. The second important implication is that these PCR forecasts are actually quite skillful, perhaps more than we were expecting going into this study. And this is certainly true during above average snow years, but also during short lead times, like an April 1st 0-month lead time forecast. But in contrast, CASC SMA is better at longer lead times, especially during these dry years. And so these complementary behaviors of the two models and where they're skillful and when they're skillful may suggest that moving forward, a better forecast could be produced by leveraging different models at different lead times or in different locations under different snow conditions to produce a better final product. Thinking about what this means for model skill under declining snowpack, we have several hypotheses about what is affecting model skill in these instances. The first is that the vulnerability of snowpack will be the primary or one of the primary drivers of forecast skill into the future. But this is complicated by things like the quality of forcing data. For example, how many SNOWTEL stations are in the regression equation, or how complex is the terrain in that forecast point that the gridded data are trying to represent. But also things like the model process representation. Can nonlinear streamflow response from a lower snowpack be represented by the model, either as designed or in a constructed way? And does the model therefore capture changes in future snowpack? All these things are very challenging to disaggregate and largely outside of this study, but we can get a sense for the long-term forecast scale trends, which may give us some insight to these things. To do this, we follow a methodology by Pagano, which used a 20-year rolling window to evaluate Nash-Sutcliffe, this specifically for PCR for historical forecasts. If we extend this analysis and do this across our 4 regions, and then aggregate by lead time, which is shown in the thick grayscale lines, we find that in some regions, there is statistically significant declines in the PCR forecast scale, particularly in places like the Pacific Northwest, but also in the Missouri and in the Colorado Rio Grande at some lead times. Other instances are less clear. These dashed lines represent no statistical significance, but we also see some increases in forecast scale. A similar analysis with the CASC SMA model is a little more complicated due to shorter continuous period of record, but we do find that there are similar trends in CASC SMA forecast scale. So the main conclusions from this historical analysis are, one, that the conceptual model, CASC SMA, generally does not outperform the statistical model. And clearly across our period of record, snow has a high predictive power, leading to these really robust PCR forecast performances, at least during these snowy years. But we do see that CASC SMA is better at longer lead times and during low snow years. And so perhaps as future snowpack declines, maybe a physical model, or at least a physically motivated model, might be more skillful. But skills also degrading through time, suggesting that these relative model skills may be changing with respect to one another, which raises questions about how these models will do under future decline. And so in our second study, we try to answer that question directly. And so the title of that study is The Potential to Mitigate Skill of Seasonal Water Supply Forecasts from Snowpack Loss in the Sierra Nevada. And so we asked 2 questions building off of the first chapter, the first study. Question 1, as snowpack declines, are statistical seasonal water supply forecasts degraded into the 21st century? Does this hypothesis play out? And what is the value of supplemental observations in mitigating water supply forecast skill degradation in different basins? So beginning with this first research question, we're going to answer it using the Variable Infiltration Capacity Model, or VIC. VIC is a physically based semi-distributed model that is run on a macro scale. This model was run by folks at Scripps that used LOCA downscaled meteorological data from 30 global circulation models across a spatial resolution of about 6-kilometer grid cells. This model was run from 1950 to 2100 under historical and then low and high emission scenarios. And then from this data set, we pulled 10 GCMs that were identified as best representing important parts of California's climate. So we're specifically now looking at basins in the Sierra Nevada. And this is modeled after the California Department of Water Resources Bulletin 120. The B120 is their water supply outlook product. And from their water supply forecast points, we selected 26 corresponding Huck 8 basins shown here, which span the Sierra Nevada into Northern California, and together represent 60% of California's developed water supply. We simulate the recreation of California DWR forecasts. Cal DWR uses a regression technique very similar to the NRCS. It's a multiple linear regression that's slightly different than the PCR, but functionally the same. And so we use this PCR method to retrospectively recreate these forecasts during the historical, and then simulating those same forecasts into the 21st century using this simulated VIC data. So we're in a completely modeled environment. The way that we simulate these forecasts is by selecting the grid cells which overlap with existing observation stations, and then using these grid cells as surrogates for future point observations. We then develop the PCRs, training them on April through July simulated runoff from that same VIC model for February 1st and April 1st forecasts for all 10 GCMs for 3 approximately 50-year periods, ranging from the historical on through to the end of the 21st century. Our results from this analysis show that there is steady skill degradation from the historical on through to the late 21st century. This is true under both a high and low emissions scenario, but is particularly amplified under the RCP 8.5 high emissions scenario. To help give a sense of what the units of Nash-Sutcliffe translate into for an operational outlook, we calculate that a change in Nash-Sutcliffe of 0.1 is correlated with an increase in the mean absolute percent error of about 2.5%. And so across these basins, which have a mean April through July streamflow volume of about 300,000 acre feet, this translates into an increase in forecast error of about 7,500 acre feet for every loss of 0.1 NSC. And so if we look at the change from the late 20th to the late 21st century and plot this out across the basins, we can see that there are some basins, particularly in the northern Sierra, where this loss of skill is significant and approaches 0.4 NSC. This represents a loss of skill of about 40% relative to the historical period. In contrast, in the southern Sierra and the eastern draining basins, we find that forecast skill is relatively resilient to forecast degradation over this time period, which is an effect of elevation buffering. If we look at the change in forecast skill as a function of the change in snow water equivalent, this figure here shows the change for the early 21st century in the small dot for a given basin, and the change for the late 21st century in the big dot. And so we see that there is a strong correlation between change in scale and change in SWE for that February 1st and April 1st forecast, though by April 1, there are other factors that are likely affecting this relationship. So if we look at, if we look at techniques for mitigating this loss of skill within this same modeled environment, we evaluate two. The first is introducing additional simulated data that represents a remotely sensed product. And so this method is modeled after the Airborne Snow Observatory. ASO uses a technique where they combine high resolution snow depth measurements with snow density modeling to represent SWE across the entire basin. We simulate this by providing our regression models with SWE for every single grid cell within that basin to represent this ASO type flight. The second technique that we evaluated is the inclusion of soil moisture data, where we provide those same regression models, or sorry, a different set of regression models, these soil moisture simulations at existing precipitation stations. The results from this analysis for the Airborne Snow Observatory are shown here for the early 21st century across low and high emission scenarios, where we have the forecast improvement in Nash-Sutcliffe as a function of the forecast skill loss across those same time periods and emission scenarios. These dashed lines then represent sort of this replacement rate. So the ability of this enhanced forecast to replace the loss of skill, where 100% represents a 1-for-1 and 50% represents the enhanced forecast replacing 50% of the lost forecast skill. And so we find that the ASO technique in the early 21st century, at least, can introduce significant skill back into these models, somewhere in the range of 25 to about 75%. And this is true across both emissions platforms, but that there are some basins where there's actual loss of skill from this enhanced technique. suggesting that a localized approach to an ASO type flight for buffering skill would likely be needed. We can also map these results spatially. We find that the greatest improvement is found in the basins that are also most at risk. If we look at how soil moisture observations affect the forecast skill now across the late 21st century, we find that that they're able to introduce marginal amounts of skill somewhere in the range of 10 to 25% of the lost forecast skill, which is less significant than the ASO, but it does have the ability to introduce skill that might be lost from dwindling snowpack. And again, we see that a lot of these basins that were most susceptible to loss of skill respond best to this enhanced forecast technique, whereas historically accurate and more robust forecasts in the southern Sierra do not respond as well to the introduction of soil moisture simulations. So our main conclusions from this second study of future water supply forecast skill in the Sierra Nevada are: one, that water supply forecast skill is likely to decline significantly throughout the 21st century, with average declines through the end of the century of about 20%, and in some instances upwards of 40%. And that the lower elevation northern Sierra is most vulnerable to loss of skill. We see that the loss of skill is well correlated with loss of snowpack, and that because of this, higher elevation basins are more buffered from loss of skill. Catchment properties may also accentuate or buffer this loss of skill, including things like base flow index. However, we may be able to buffer this loss of skill through the inclusion of additional observations or predictor variables in these regression-based equations. Specifically, remotely sensed snowpack products may replace anywhere from 25 to 75% of lost skill in the first half of the century, but with dwindling returns through the late 21st century. Some of this may be picked up by soil moisture, which could improve these forecasts by 10 to 25%. So some take-home points from these two studies and thoughts on how we might improve water supply forecasts in a world with less snow. So first, we argue that lower snowpack represents a threat to the skill of conventional water supply forecasts, and that as we lose snow, we're also losing predictive power of snow in both regression-based and conceptual models. But we may be able to improve existing operational forecasts, which of course represent the lowest hanging fruit. We may be able to do this through new observations and predictor variables, but this is of course challenged by length of record, as well as sort of institutional inertia. But forecast coordination or an ensemble of multiple models may be promising. Other options include advanced statistical analyses or machine learning, but clearly improving operational products is a long game. And so to help us move in that direction, further model benchmarking studies will help us better disaggregate forcing data from model error, so understanding where our errors are coming from in our models. These studies may also help us quantify forecast uncertainty, which will be more important as we move to a more variable hydrologic world. And they'll also help us better understand model performance under non-stationary conditions. But each of these are incremental pieces in strengthening the scientific case for improving our operational procedures and products. So with that, I would like to thank the Southwest Climate Adaptation Science Center, as well as folks at NCAR, Andy Wood and Andy Newman, who helped us run SAC SMA for the model benchmarking study. Angus Goodbody and Jolene Lee, who are both co-authors on this as well, gave us helpful feedback and conversations throughout this study, as well as folks at the California, Nevada, and Colorado Basin River Forecast Centers. So thank you for your time.
Thanks, Josh. I think that was a really great presentation distilling a lot of work. We have as much time, probably more time than we need to discuss some of this. My thoughts would be to start with comments, concerns about the methods and what was done, and then maybe move on to thinking about how to make this as most useful as possible to the folks that are on and not on the call. But I have you all, so you're unmuted. You can unmute yourself now, or you could ask the question through the chat window. And I guess we'd just like to get some feedback from a lot of folks that have not seen this before.
Hey, Ramesh here. Quick question for you. First of all, like, what was the reason for considering only Nash-Sutcliffe efficiency coefficient for this study? What was the what was the rationale behind that?
Sure. We also in the manuscript we do consider other metrics as well, but it is our primary metric of choice. And we did play around with using things like relative root mean squared error, as well as MAPE, but felt that something that normalized for the variance in the observed stream flow, which turns out to be a major source of forecast error when you're looking at something like root mean squared error, was really valuable in our instances, looking across so many basins that varied by so many orders of magnitude.
Yeah, but many of those previous studies, like what researchers have found that with the same data, like if you use Nash-Sutcliffe efficiency versus other efficiency, like the performance of the model varies a lot. If you use Klein-Gupta efficiency or a volumetric efficiency versus a persistent index or percent bias, and then use the Nash-Sutcliffe efficiency, I think what happens is, like, for the same set of data, the performance varies a lot. So I think what you have done is great, but in addition to this, I think it is necessary to consider all other efficiency index and run the model and see where you are at. That's how I think that's what it needs further, I think.
Okay. Yeah, thank you for that feedback. And that's certainly something that's easy enough to do. I think in the one comment I do want to make that I didn't make in my first point is that in a benchmarking approach where we're specifically comparing one model with another that were both essentially trained and are predicting the same data, I think it makes for an easier comparison between something like a Nash-Sutcliffe between one model and the next when you're using the same forcing data.
And the other question I have is, like, so you converted all the data into the principal components. So what are those primary principal components? Can you tell me about that? Like, what is the first principal component, second principal component, and third principal component? Like, when you converted that into principal component, how did you make sure that the variations of the data, that kind of preserve that variation? So how did you make sure on that? Can you talk about that?
Sure. Yeah. So we followed a method from David Guerin of the NRCS for the principal component regression forecasts, and did consider using multiple principal components and evaluated individually their statistical significance and value of including those into the model. And in all instances, save for, I think it was about 3 forecasts, the first principal component was the only significant one, and so it was the only one included in those forecasts.
So what is the percentage of data that was aggregated by first principal component? The contribution of the data by the first principal component, how much was that?
Sorry, could you ask that question again?
Like, when you consider only first principal component, what happens is when you convert into the principal component, like, it attributes certain components, certain percentage of the data, those attributes are underlie
Sure.
goes into that component. So what was that percentage?
I don't know that percentage off of the top of my head because we're running, each of these 50 or so basins has multiple lead times that we're running. So that varies for all 200 or so PCR models that we're using here. But it was
okay.
Yeah. So Ramesh, this is Mike Bettinger. So there were literally over 200 or something like that. I think that's right. Answers to your question. It wasn't he didn't do a single principal component analysis. He did multiple principal component analyses, one per forecast lead time for each of the basins that he looked at. So there is not a single answer to your question.
So that means like you use those components and develop that forecasting models. I afraid like what happens is if you do not consider, the primary components that attributes like at least 90 to 95% of your original data, some of the variability may get lost in between. So that type of things, I don't know how it was done, in your analysis. So I'm curious,
Sure. Yeah, I'd point you to the David Guerin methodology, which we studied, which lays out selection of principal components for specifically water supply forecasting.
Yeah, do understand that Josh was trying to reproduce as much of the NRCS forecast models as he could in a sort of standardized way that he could apply directly to all the basins and the like. So this wasn't that we came up with a bright idea of PCR. He was trying to reproduce the NRCS method.
All right, thank you.
Thank you for your questions. I appreciate it.
And those that are not as sort of up on this, essentially you're trying to take out the covariance of precipitation and snow water equivalent. In our method, those are the only predictor variables. So, and they're obviously very correlated to each other.
I see.
But it's a very good point. I mean, it's something that, there is a certain amount of percent explained in each of these. And in your first point as well, Ramesh, makes me think that maybe we should release some of this data so that others can go back and run whatever, accuracy sort of metrics they want to. To pick up on Mike's point, one of the reasons we did so much with Nash-Sutcliffe efficiency is that's what others have used in similar studies. It's really been the focus of both sort of previous investigations of PCR models, like the Pagano work, but also like the more recent benchmarking type papers comparing multiple models. But those are great points.
I think that's how, like, when I see all those research and then try to use different coefficients and different parameters, and for the same set of data, if you use one set of parameters and then result goes all the way other side and then with another on other side, and somehow unless we have like multiple parameters, at least more than 10 parameters, if we use and develop and forecast the model, then we can say, okay, there is something in there, so we can kind of get some additional insights into that. But anyway, that's great study. I like it. And the other question I have is, did you guys do any sensitivity analysis, by the way? Like, while conducting the sensitivity analysis, like what variables exactly is having issue here? Like regarding with the elevation or precipitation or SWE, or what variables is kind of playing a dominant role here for the lack of accurate forecast in the long term? Any idea on that?
Well, I'll let Josh answer more, but I think it's very difficult to answer that with the PCR because it's just kind of everything in the hopper and very hard to pull apart. But maybe Josh can calibrate on his shuffle complex evolution, calibration of CASC SMA, and whether, I know you spent a lot of time thinking about that.
Yeah, so we did recalibrate. So we used a standalone version of Snow 17 and CASC SMA, developed by, or sort of modified by researchers at NCAR. And we recalibrated that using a shuffle complex evolution, including, I believe it was, including the snow depletion curve is probably somewhere around 20 parameters. And so we did that for each study basin for each forecast lead time. So there was a separate model structure so there are 204 model structures.
And so some parameters are probably more sensitive sort of globally across the models, but then obviously, you know, some basins and models are going to have certain sensitivities that other ones would not.
Okay. Thank you, guys.
You're welcome.
Hey, Josh, it's Andy Wood.
Hey, Andy, thanks for joining.
Nice presentation. I have a few questions. I'm going to try to remember what they were. But I think they're all pretty quick. And the first is just, I wonder if you could chat a little more about the extent of cross-validation, both in the statistical and in the model-based cases. I realize it's kind of a whole range of things that can be done, and it's not always possible to do all of them, but that'd be helpful. The second is if you can mention the sample sizes on the ASO work, maybe if there are uncertainties due to small sample size. And then lastly, as a way of potentially offsetting losses in skill, I didn't notice that you mentioned climate or weather forecasting improved, and I wonder if you could comment on how you see potential for that being one of the improved inputs.
Sure. Yeah. Thanks, Andy. So I'll take these one by one. So for the first study, the benchmark analysis and the cross-validation of the models, we calibrated to the 1990s for the CASC SMA model, and then ran it for the remainder of available years from the CAMELS data set. An important distinction, however, is with the PCR model. We did not have separate cal-val years, primarily because of concerns of us then subdividing the data into wet and dry years and just limiting our sample size too much to be able to say anything significant. So in that sense, the PCR model is likely going to be biased and more skillful than CASC SMA because of our experimental design decisions going into that. The second question about the ASO sample size. Let's see, so we developed new ASO models for each basin. So there's 26 sample basins or study basins, and then did that across the early and late 21st century periods, which were themselves different forecast period, different forecast models that we developed. And so, and in doing so, as I explained, we essentially provided SWE to the model for every single grid cell within that basin to simulate that ASO type flight. So yeah, so and then sorry, go ahead.
Oh, and yeah, so that's a little bit similar to the Rosenberg approach with
Yes.
kind of like synthetic ASO data. So you could have quite a big sample size.
Yeah, synthetic's probably a better word. Yeah, so
Yeah.
So each, right? Yeah.
And then the last, so I guess on the first, well, I thought of another question, but on the first, sorry, the first comment on the cross-validation is it might be worth looking at that with a kind of proper jackknife approach to get the prediction error, because I think that can change conclusions potentially. I've seen a lot of shrinkage in skill once you do a full cross-validation, particularly on the statistical methods. And then kind of related to that comment and what the earlier questioner asked about the use of the metrics. If you use a metric that's strongly associated or affected by bias, it will tend to make the model-based forecast look somewhat worse. And so I think there is some case or argument for using multiple methods and seeing if the conclusions hold up across, or metrics, seeing if the conclusions hold up across the metrics, which would make them stronger. So anyway, those are just two comments. And then the last was the question about the weather and climate forecast, particularly like subseasonal climate forecast.
Yeah, thank you for your comments on that. We'll definitely take those into consideration. But we did not work on folding in any climate indices or weather forecasts into this model, but I assume it would probably prove to be fruitful.
Well, I'll add on that, Josh, because I actually think you talked about this a lot in the presentation you gave a week ago, but you pulled it out a lot of here, which was, I think, necessary. But just showing that prognostic error and the sort of potential improvement you can get from improved post-forecast precipitation was pretty sizable, right?
Yeah, so if you define climate error as the difference between like our standard retrospective forecast and the prognostic forecasts, right? Like how much better does the model do if you run it with data through the end of the forecast period? That would suggest that that by including like an accurate climate forecast into the predictor variables, that you would be able to improve things considerably.
Yeah.
But especially at longer lead times, I guess, would be where it would be most valuable. But we didn't evaluate that at all in the second study, looking at the VIC simulated forecasts.
Cool. Well, thanks. Very interesting.
Thanks for your questions.
Thanks, Andy. I appreciate that. I have a feeling we'll be hearing more about the jackknife suggestion.
You might.
Other questions, comments?
Thoughts about the way forward.
Right, yeah, we can open it up more broadly to just, one thing we'd like to do is make this as useful and put it in the right people's hands that would find it useful. So any comments about that would be appreciated. Our plan is obviously to submit these as academic articles and peer review, and then we'd like to do some type of management brief where we put this down into a page or a page back and front and have that a little more approachable. So that if that makes sense to folks or doesn't, we'd appreciate any comments on that. And I think another thing we've considered is giving more targeted or taking parts of this and representing it to folks again, especially digging into a lot of the details that Josh didn't have time to today. So any suggestions about who might be interested in parts or all of this talk would be also appreciated.
Just quick question, Adrian and Josh. The environment in which you guys conducted this data analysis, was that in R or Python, or what was the environment like? Which software did you guys?
Yeah, it was run in the programming language Python.
Python, okay. So that means all the coding and everything you guys have Python. So is there any way that you guys would like to release that code for public use, or how things will work out?
Yeah, I think it's something that we as co-authors need to discuss, like our strategies for considering that.
Okay.
I think it could make sense. I mean, keep in mind the whole SAC SMA Snow 17 stuff still lives in Fortran land. We didn't recreate that. It would just be the sort of the code to process all of the forecasts. But I do think the suggestion to release the data sets and maybe whatever scripts are associated with creating those data sets is a valuable one. I could see that making a lot of sense.
Yeah, that's what I was kind of thinking, if you guys can release that and we can play with that around and then see how can we, take best advantage of that. That was kind of my idea here.
Yeah, well, we might follow up. Go ahead, Mike.
Oh, I was just gonna, if nobody else is gonna pop up, I'd like to return to Andy's comment about the sort of climate forecasts as a mitigation scheme, essentially. And I'm just curious. We did talk about that quite a bit earlier in the project, and that trying to sort of sort out how that might look. And frankly, one of the things that we discussed back, and I'm kind of saying these things in hopes of getting some feedback from folks. But one of the things that we talked about, well, Josh talked about, talked about the possibility of sort of leveraging models off of each other to take most advantage of the statistical methods when they historically do well, and the physically based methods when they do well, that sort of thing. Well, one of the things we did talk about was the prospect of starting to fit models to the climate, two subsets that were defined by climate forecasts, the seasonal forecasts and things like that. And so that was kind of how we were thinking about how you might build those forecasts into the mix. And having said all that, I appreciate your comments, but I'd like to just ask a question of you and anyone else. But so right now there are kind of two major climate forecast variables. One is precipitation, looking out, and one is temperature looking out. Lots of other things, but if you start with those, I'm just curious. I think we have better skill with the temperatures, and the temperatures historically haven't been drivers of some of these models, the statistical models in particular. But it certainly seems to me that if we could get a handle on how to build temperature looking forward this season into the models, that's going to that might buy us some time as the temperatures trend warmer through decades. So anyway, long thing, but I'm just curious what that's kind of partly where we were coming from.
Yeah, I mean, I would agree with that. I think there's probably more potential in temperature from a skill perspective than precip, even though precip is a more prominent driver. And we did have Gus Goodbody, I think, was on the call, and he could probably comment too. We had a paper embedding some temperature forecasts from the NMME into PCR-based predictions for kind of the Southwest in the Rio Grande in Colorado, and did find some marginal skill improvements when you did that in some cases, but it was kind of down in the 0 to 10% range of variance explained. And Gus Goodbody was part of that study along with people from ECMWF. It was led by me and Flavia Lehner, who was a postdoc. He's a climate scientist. But we've done more work down that vein, also with precip, with the reclamation in the Upper Colorado, and looking at conditioning sort of model-based DSPs with NMME-based predictions, and we've also seen some benefits there. I personally think we left some skill on the table. Like if you look at the RFCs now, they embed weather forecasts into the seasonal predictions, and then to some extent, increasingly with like the HFS system, they're starting to embed more medium range, like the GFS forecast going out to 15 days. I think less use of the seasonal climate forecast, but there is this kind of sub-seasonal scale where there's, I think, achievable skill, like in the days 10 to 20, weeks 2-3, on precip and definitely temperature, that I could see adding a lot of like a measurable increase in skill, in the, particularly in the spring. when climate matters the most. So I see some potential there. I recognize that increased, better watershed-based observations like ASO can also be a benefit, but I think that, the climate forecasts are really going to help us when we really do lose the snow predictor. That's just from my recent experiences, I guess.
Sure, sure. And hopefully by then we'll have, we'll be in a better position to do it with the climate forecasts. Yeah.
Yeah, I bet others on this call also know, more than I do on that topic.
I think I unmuted Gus, and I see Steph may want to join in.
Yeah, 'cause I just wanted to comment on this, that I think this is one of those situations where it's going to be very place dependent. In some parts of the Colorado, you may actually get some skill out of the precip forecasts. In parts of the Sierra, they're not as good, at least currently. So it may be one of those things where the time of the trade-off from including this information versus not including the information shifts outward. It may also be something where it makes sense to do, and I think we all discussed this on the project team, use an approach more like CASC has taken, saying, okay, well, let's run it forward with a dry scenario, a moderate scenario, or a wet spring, and see where that puts us.
Yeah. I don't want to, if I could just respond really quickly, I would totally agree that it's kind of a work some places and sometimes a year, not other places and other times a year. And we had a paper a number of years ago on looking over the entire camels data set, actually something like it, like, probably, what was it, maybe 500 basins across the US at the dependence of runoff predictability on climate versus watershed predictors and how it varied throughout the year, and to what, basically what the elasticities of runoff skill were to climate versus initial conditions. And it completely backs up what Stephanie just suggested. But I also want to comment really quickly, that's also problematic for the operational world in a sense, because you don't necessarily want a prediction model where predictors jump in and out, from period to period, because it kind of makes it hard to track why a prediction might have changed. If you have one predictor one month and not the next month, and then the outcome change, you can't say it was because of a change in one predictor going up or down. And so there's a little bit of a tension there between using all available data in a data-driven method to optimize skill versus holding back to a more stable prediction model. And again, the people from NRCS and other forecast centers can comment on that, but that's one thing I have noticed in the past couple of years of dealing in this issue.
And I'll waiting for Gus to jump in because he sent me a note saying he wanted to make a comment. But...
Yeah, I'm on now. Can you hear me?
We can.
Yeah, I have a different question, but I can just comment on Andy's notes that the storyline about why forecasts are changing does remain important in the operational world. And yeah, I totally agree with what Andy said. I'm not saying that can't be changed, and I think in a lot of ways we're moving away from that a bit, because there is the other side of the argument, of course, is, hey, if it's better skill, even if it represents a little bit of a break in the storyline from the previous day or the previous month, then why would you turn away from that? So I mean, it is balancing those two things. That is one of the challenges to bringing it really to bringing some of these new ideas into operations. But I also wanted to make a comment about the idea that, some of these climate forecasts or short-term weather forecasts might be more useful in some areas than others. And while, of course, it would be great if, one approach just worked everywhere really well, it's okay from an operational standpoint if certain techniques only work, you know, in certain areas. If we can, you know, if we can identify where those areas are, then that's reasonable. It doesn't have to be a solution that you know works everywhere per se.
Thanks, Gus. Did you want to ask another question as well?
Yeah, I did. I had a question for Josh. It was kind of more back in the nuts and bolts of the benchmarking effort. And I caught it from some of the slides, but I just wanted to verify that what I saw was correct. So with regard to the benchmarking of the CASC SMA model, so did you guys run that then using DayMet as forcing? And then my question is really just about how did you calibrate it, and then did you just run the model unattended essentially to get the results that were then compared to the statistical modeling?
Yeah, you're spot on. So we forced it with DayMet gridded products using a lumped base and mean, and then calibrated that in the 90s, just looking at daily stream flow for the calibration, using, I think, an RMSE metric. And then use those optimized parameters to run the model unsupervised.
Okay. Yeah, and that's what I thought, and I know that that's kind of how it has to be done to some degree. I just wanted to bring up the fact that it becomes harder to draw conclusions about, you know, the way that model is run operationally, just because it tends to be heavily modded during operations, and that can really change, you know, the outcomes, of course. And I know that the fact that the model runs that way makes it very difficult to, you know, objectively recreate sort of a comparable forecast like as would have been generated in operations. I mean, that's always been one of the real challenges. I know, you know, Andy has worked on some of that a little bit with some success, but just wanted to, when you do it that way, of course, we don't want people to draw conclusions about, you know, the operational forecasts that are issued. And I think that goes for the statistical models too. And you pointed it out that a lot of times the NRCS will use the statistical model as guidance, not necessarily the absolute operational forecast. So those are two slightly different things.
It's a good point.
Yeah, thanks for that.
One I'm not sure we can get around.
Yeah,
I agree. It's a challenge.
Sorry. Yeah, we do. I mean, we address it directly by basically saying, you know, what are we going to do about it? We, on one hand, are pinned in by, you know, reproducibility. On the other hand, you know, reality. It does open the question of, you know, how to do these benchmarking studies, which I think also gets to the point about, you know, what accuracy metrics you use, your skill metrics. Is there a better way to do benchmarking studies like this? Because I think this is the future that Andy and the group is sort of paving, is trying to really, as best you can, compare these models, because it's so hard to move forward unless you can really say quantitatively where strengths and weaknesses are.
Yeah, that's a really interesting point.
Yeah, I've always been a fan of that over the loop approach, in part because of the benchmarking potential. The one thing I'd comment, you mentioned that it is one of your conclusions that it, you know, maybe the best case going forward is that we have these two approaches and maybe multiple approaches beyond that, and that, you know, you may be best off just sort of picking and choosing or merging the different, you know, statistical model-based, maybe different versions of statistical as the NRCS is working on now with Sean Fleming having joined. And it's interesting because years ago, until about 2012, you know, it was kind of the common practice to, you know, discuss and merge the model-based forecasts and the statistical forecasts, and that coordination practice diminished a little bit. And Tom Piano and Rashawn, another NRCS forecaster, and I and Kevin Werner wrote a paper on that back a little while ago. But it was a change toward that maybe had left some skill on the table when moving away from the possibility of having both forecasts or multiple forecasts to choose from, where the forecasters actually know to some extent how well they do in different places. You may have kind of backed away from, our most skillful potential forecast operationally. So maybe that will come back, and maybe NRCS will do it through multi-modeling.
Yeah.
That's definitely the direction we're headed. We're putting a lot of effort into that right now. And in a sense, I do see it as a return, to you, rather than this idea of one model and that's it. We know that's not the best way to go. So I know it's easier to only deal with one model per organization, say, but it's not probably the best we can do with regard to the water user community. So returning to a multi-model approach, and of course that takes more infrastructure and time to do to some degree. But I actually see it as we want to bring not just the models that we build and run to the table, but also any other legitimate model that's out there should be potentially brought into the operational, at least the decision making. With I want to know what's going on in these other models and start to understand better about their strengths and weaknesses. So I see it as a return to kind of a more formal and maybe objective coordination across agencies too.
Mm-hmm.
That's great to hear. That is very much supported by, I think, Josh's findings in terms of strengths and weaknesses.
Hey, Adrian, I have a question, purely procedural, but do you know how to save the chat comments in the Zoom?
That is something I've done.
There's some pretty good ones that folks haven't necessarily spoken up about.
It'd be great to bring up the ones we can. We have about 15 minutes left, but I will find a way to do that, Mike. I have not done that before.
Yeah, I have neither.
I think a copy and paste.
For instance, Mike Anderson was sort of asking about, and this is my at least interpretation, as sort of other variables that if we monitored, they might be useful, and I'm putting words in his mouth, but that included sort of a snow altitude distribution as opposed to just a total or average SWE, something that gave you a better sense of high versus low snowpack, that sort of thing. And then another one was just sort of solar radiation. Is there room for that?
Yeah, and I was reading these questions, so maybe we'll take the first one. I think that, I guess where I thought that could go was the fact that a lot of these regression-based forecasts don't have temperature in them at all, for one thing. So is the temperature skill, I don't know the answer to this, does it really come in and the rain-snow transition? Or is a lot of that skill coming through the ET loss and the driver of the PET models?
There's also obviously the third one, which is just sort of early melt.
Right. We're driving melt.
For those early, the January, February, March, even March forecasts looking out to April. You kind of want to know how much of that snow that I'm already seeing or anticipating is still going to be snow on the ground by the time we get to April.
I think that drives to Mike's second question, which is like that temperature skill is going to be more beneficial in some snowpacks probably than others, and depending on how the model treats it and all of that kind of stuff.
And I suspect one of the things we would see too as well is that if you put temperature into the model, it would actually be proxying different things in different locations, which is fine, right? In some places it might be looking at rain snow partitioning, in other places it might be ET.
Yeah, in a regression based approach, it's certainly
exactly
just a lump.
Yeah.
But maybe elevation banding, or I don't know. I'd have to think more about it. The problem is you don't have ways to train. These things are so sensitive to your ability to train them. we have very limited streamflow data to train these models is a major issue.
Well, but yeah, I mean, sure, but you guys already were dumping in soil moisture as a, which is a whole new variable for the California forecasts that you were using. And so you could imagine sort of, okay, I'm instead going to swap in some sort of, I don't know what, average, I don't know, high versus low ratio of snow, or some sort of weighted elevation, center of mass of snow elevation, or you can imagine cooking up something and just seeing, is there any skill there?
Yeah,
so,
and following on that, Jolene just said, who's at NRCS, I've used spring average monthly temperature as a parameter in a few statistical models that has been helpful in some instances. So I haven't seen any published research really kind of exploring that, but.
It'd be easy to extend the Vic analyses to include a temperature predictor variable.
Yeah.
Right.
I mean, there's a lot of work on that over the last 15 years about climate conditioning of seasonal forecast, and NRCS funded work looking at using predictors that were kind of indexes of climate system behavior, like the Trans Nino index in the Northern California. They've used SOI and other things like that, and then since dynamical model forecasts like CFS and MME have gotten slightly better, I think there's been more interest in bringing those in, and they're, the trace weighting type approaches go back probably 10 or more years, with the ESP conditioning. And then the other strategy there is like weather generation conditioned on climate forecasts or reanalysis based indexes. That's also been done, like Balaji Rajagopalan has published on that, and other people. I think there is a lot out there. My basic sense is it's difficult. There are these predictors and they have their own skill, and then getting those from skill to the water supply context is a little bit more work. And so, by the end, you end up with kind of a slice of skill improvement. It's maybe like 3, 4, 5, 6%. And it's really only through adding multiple slices, a slice from an added climate predictor, a slice from an improved watershed observation, maybe another slice through some post-processing that removes bias, that you maybe get up to something that's significantly better. And then, maybe a better model is a big part of it that has been actually calibrated to, specifically, for instance, here's one idea, calibrate to produce the runoff volume that you want to forecast versus calibrate to a daily NSE, which might or might not have an unbiased April through July runoff. That's not an explicit objective. So, there's this whole suite, kind of like a, Swiss Army knife of little tools that can be thrown at it. And some of them may add something, particularly with the climate, but there has been quite a literature on that. I'd be happy to chat more about it. And I'm actually wondering if there's a good review. I think Eric Wood recently was part of a review that looked into climate forecast use within seasonal forecasting context. I also co-edited a big special issue in HES on seasonal streamflow forecasting that had like 45 papers, most of them probably more from Europe, using like ECMWF inputs from System 4, System 5. So there really is a lot out there. It's probably harder to figure out what's been done, so you don't redo something, than it is to actually do something new. Try a new experiment. But it's probably worth it too to go back through it. Even in California, Kevin Hay over at California DWR and working with CNRFC, I think published a retrospective seasonal skill assessment on HEFS forecasts. It came out a few years ago. that's maybe another reference point for the California work.
Thanks for that, Andy. I think my point wasn't so much that it hasn't been done. I was just wondering if that next step of bringing it back to like streamflow forecasting and PCR land and the value of that. I also agree with your broader point, and it's consistent with a paper I published about trying to bring soil moisture into these regression forecasts, which is that it's hard to get skill, partially because they start fairly skillful, and
Yeah.
partially because you're not, you only have so much information you can really bring past that. But those are great points.
I was thinking there was a paper I used to cite that was from 1948 in the Western Snow Conference proceedings, where they showed that in addition to using like SWE measurements as a predictor for seasonal volumes, if you use antecedent streamflow as a proxy for soil moisture, you can bump the scale or narrow the uncertainty, So that was 50, almost 70 years ago, people were kind of thinking about these things.
Yes, and I've certainly heard some anecdotal information from folks in Colorado that they go up to a conference room on a certain floor and look out and see where the snow level is at different times of year, and that actually gives them a decent ballpark.
It's that hard, for sure.
Yeah. So in trying to incorporate some of this snow level work might actually be really effective.
Yeah, and I had one more anecdote that I kind of recall from conversation with Brent Bernard, who's on this call, CBRC, formerly CBRC. But, and it wasn't like systematic, but even observations like when the, squirrels start to appear in the springtime tells you something about the ripeness of the pack and whether it's like draining internally and things like that. Like, obviously you're not going to like measure that systematically, but just these little kind of, observations, I think tell you a little something if you're forecasting in a local basin. That always stuck in my mind as something I would never have thought of. But it's interesting.
We can remotely sense the squirrels, then we can. No, Mike Anderson asked a question about fall soil moisture and frozen soils. And I don't think we really played too much around with this in terms of Josh's work, but I did do some of this for a previous regression-based analysis. And you do get some skill out of fall soil moisture, but it looked like the real skill was taking soil moisture right around the forecast date. And you got more skill from that than fall stream flow. That was, a handful of basins across the West. I mean, there's certainly a lot of like physical intuition that if you have a dry fall soil moisture, you got to fill it up. And if you have frozen soils, your runoff generation processes completely change. But how well that's taken advantage of in our current models, I would say probably not well in terms of leveraging observations.
Yeah. I think there is an effort within the model-based forecasting centers to kind of go through and make sure that initial soil conditions in the fall before the freeze up are reasonable, just for precisely the reason you suggest. You want to make sure when you come out and the snow starts melting, you have a proper deficit. And I was certainly never involved in that, but I do know that's something that forecasters pay a lot of attention to.
Where they look at observed soil moisture to tweak that?
A little bit, yeah. I couldn't actually, somebody from CBRC could talk more about this or more intelligently about this, but I think it's a little bit less observation-based because the soil moisture observations are still pretty scarce, and more looking at kind of the climate that occurred throughout the fall and whether the model states are reasonable and consistent with what you would expect given the kind of, rains or temperatures you might have had like through September, October, November, and then in late November or early November sometime, kind of trying to true everything up a little bit in case anything looks out of whack.
Yeah, and that makes sense. Yeah, we are just, the NRCS has, and Jordan Clayton was on the call, the they've done a really outstanding job of building more soil moisture capacity, but it's still a sensor that's this big, you know, and it's a tricky one for sure.
Yeah, potentially useful eventually.
Mm-hmm. Are there other comments? This has been a great discussion. There might be somebody kind of holding in the back that wanted to ask a last question or comment. Well, my plan is to post this video and spray everybody with another email saying that I did that, and then we can share this. I think our whole group, Steph and Mike and Josh and myself, would be very interested in feedback or, you know, thoughts you might have afterwards, you know, thoughts other people that you share this might have. So we really do appreciate all of your time and this great conversation. So I think with that, I'll call off the Zoom unless there's any other comments. Have a wonderful Wednesday, and I will be in touch regarding all of this. So thanks again, Josh, and rest of the team. And thanks everyone for your time.
Thanks, Adrian.